Non-homogeneous ODEs. In the previous video on homogeneous ordinary differential equations, we looked at solving ODEs in the form d2y by dx squared plus p lots of dy dx plus qy is equal to 0. Notice the equal to 0. Now we're looking at ordinary differential equations where the right hand side is not equal to 0. So now the general solution of our equation, when we had homogeneous ODEs, y was equal to the characteristic function. This time we're going to have the characteristic function plus a particular function. So to choose what the particular function is going to be, we have to do a bit of trial and error. So to start off, we can take a good guess from this table. So if our right hand side, f of x, so here we're going to have our differential equation in the form d2y by dx squared plus p dy by dx plus, I think it was q we used last time, y is equal to f of x. So this is the f of x we're talking about here. If f of x is a trigonometric value with cos or sine, then our particular integral or particular function is going to be a summation of cos and sine or it could be cos and sine multiplied by x, our variable. You can just see there. The other functions we could have is an exponential, so again we'll just have a simple exponential, or if we have our function exponential multiplied by x, then we will have a polynomial multiplied by our exponential. Just have a quick notice about the differences. In the first with trigonometric, we've got a here, and then we've got alpha and beta. So we will have to work out what alpha and beta are from the ODE. Now, this section is a bit more complicated, but it is basically if we have a polynomial multiplied by an exponential multiplied by a trigonometric function, then this is going to be what our particular integral will be. So it will be x to the power of m, where m is a constant to work out, times by a polynomial of x times by an exponential, and in the brackets we'll have polynomial times by cos plus another polynomial times by sine. So that's where it gets quite complicated. But we will have a look at these first three, these ones first. So why don't we do an example? So our example is going to be actually the same as the last video on homogeneous differential equations, except from rather than having the right hand side equal to 0, we're going to have a function. Oops. Just write this out. So we have got the second derivative of y with respect to x plus 8 lots of the derivative of y with respect to x plus 7y is equal to 2x. So in the previous video we had that the complementary function, and I believe we just called it the general solution, but now it is the complementary function, is equal to c1 e to the 2x plus c2 e to the negative 3x. So we know, as I just said, that y is equal to yc plus yp, and we now have yc. That is done. If you can't remember how to work that out, that is, as I said, in the homogeneous ODEs video. So our right hand side, our f of x now, is 2 e to the x. Looking at the table on the right hand side, we're looking here where k equals 1 and a equals 2. So that means that our particular function is going to be alpha e to the x, because k is 1. So to find out what alpha is going to be, the first thing we need to do is to differentiate this. And we need to differentiate it twice. So first of all, first derivative is alpha e to the x, because e to the x doesn't change under differentiation, and then again alpha e to the x. Just going to make that a bit neater. So we've got our three values, yp, y dash p, and y double dash p. We can sub these into the original ordinary differential equation, which is this one here. So on the left hand side we've got alpha e to the x plus 8 alpha e to the x plus 7 alpha e to the x is equal to 2 e to the x. So 2 e to the x is just our right hand side from the top. Now we can solve for alpha. So 1 plus 8 is 9, plus 7 is 16. 16 alpha e to the x is equal to 2 e to the x. Now we can cancel the e to the x and cancel the 2. So that gives us that 8 alpha equals 1, so alpha equals an eighth. Oops, that should be an eighth. There we go. So now we have our particular. So our general solution, a different colour, y is equal to the complementary function, which is c1 e to the 2x plus c2 e to the negative 3x plus, and now our particular equal using alpha equals an eighth, so that's an eighth e to the x. And that is an example to find the general solution. So if we have a quick recap, the first thing that we did was we worked out the complementary function. So yc. Then we looked at working out the particular function, and I'm going to put guess here because you never exactly know, so you have to work it out from the values in the table and then test it out, and if it doesn't work, try something else. From there we calculate the constants. So here we had to find out what alpha was and what k was. K was 1 for us, is this one, and then we worked out alpha as an eighth by differentiating the particular solution and then subbing it into the original ordinary differential equation. Sorry, can't speak. And then finally we summed yc and yp to give us the general solution. I hope this has helped. Thank you very much.